Hello everyone, welcome to MACSMIN 2025. The last but not the least talk for today will be by Tatiana, now a student at University College London, who will talk about too many crystals. Please, Tatiana.
Okay, hello, Tatiana. I'm going to talk about my project on the fast generation of billions of differently looking crystals. Sometimes you can have too many crystals. So firstly, I'm going to talk about the inspirations behind the project. And then I'm going to talk about the title, why are there too many crystals? And then finally, I'm going to showcase a program where I'm creating too many crystals. Okay, so first of all, this project was inspired by a joint talk with Olga at ECM 34 last summer. By a joint talk, I mean I presented one of her slides for about 30 seconds, but that slide became the starting point of my project. The talk was called The Rise of AI After the Fall of AI. And the AI that she talked about in particular was GNoME, that we've heard about from Dan earlier today. But I've included some quotes here. It's an AI tool from Google that reported the discovery of 2.2 million new crystals, equivalent to nearly 800 years worth of knowledge. So I don't know where they got 800 years of knowledge from, but that's what they've written. The question here is, are any of these crystals actually real? And to answer this question, here is an example actually found by the Liverpool group. I know you found another example. I think this is one of the other ones. On the left is a crystal from GNoME. In the middle is an experimental crystal from the ICSD. And on the right is an optimized crystal from the Materials Project. Turns out, so using their invariants, that these crystals are perturbations of each other up to 0.0001 angstroms. But as you can see, all these elements of the atoms are different. That doesn't make sense, because if you switch out the elements of the atoms, surely the distances would change. This is just a weird example. I'm not sure what happened. But there was another group from Berkeley that also set out to answer this question. Are any of these crystals real? And they had 58 target crystals. They claimed to synthesize 43 of them. There was a review by Robert Palgrave and Leslie Shoup, and they said none of the materials produced by ALAB were new. In their words, the large majority were misclassified and a smaller number were already identified, but already known. So a better question is yes, the question still exists, are any of them real? And more important question is, are any of these crystals new? Olga Onosova talked about duplicates in proteins. She's also looked at duplicates with crystals. Here, she's found 2,311 identical files in their database. But they didn't even check for identical files. And if you look at same numbers, there's even more. And this is looking at not that those are exact duplicates, these are near duplicates. There's even more of those when you round to different numbers of digits. So the question is, why are there so many duplicates and near duplicates? Well, it's because it's difficult to compare crystals using just their files. One crystal can be represented by an infinite number of different CIFs. I think we've talked about this before. I'm just going to go through it again. Any ordered basis defines the unit cell and the lattice. I think we've seen this diagram in different versions. I think this is the fourth time we've seen it this afternoon. This time it's blue. I think that's the difference. So these basis vectors are integer combinations of my square on the left, and they generate the exact same lattice. But because they're different basis vectors, they have different unit cells. In your file, we store the lengths and the angles, and so we're going to have different files. In the files, we also store the atom coordinates as fractional coordinates. Fractional coordinates means they're written in terms of the basis. So if the basis is different, the fractional coordinates are also going to be different. On the right, we even had to add another one to fit inside the unit cell because we extended it. Well, many unit cells, which one should we pick? The obvious answer is let's pick this small square. So we want to pick minimal volume. Crystallographers try to pick a primitive cell, minimal by volume. They try to reduce it. Reducing is more complex. That basically means what the hand-wavy explanation, we want 90 degrees. We like right angles. There are different forms, for example, Niggli's form, but it doesn't matter anyways because it's not enough. Here's an example why it's not enough. We extend it, we shift one of the atoms slightly. It could be tiny, and the resulting unit cell is both primitive, so it's minimal by volume, and it's reduced. It's got a right angle. So we've got different unit cells, different files. We get a very similar crystal structure. So theoretically, I could take an input crystal, I could change the basis vectors, I could extend the unit cell, I could shift some of the atoms slightly, I would get a completely different file. This is quite an easy algorithm, so I don't know what GNoME actually did in their AI because it's a black box. I'm sure nobody actually knows what they did. I mean, Dan thinks that probably maybe they're tricking us, but I know that I can probably trick you with this easy algorithm because it's really easy. There's only 3 steps. And so I said, because it's so easy, let's just implement it. And I'm going to try and showcase. You can see that? Okay. So this is written in Python to make use of GEMI and Dash. On the left, you input your crystal. So you could select any of your own files, or I'm going to use an example here. If I remember correctly, I think this is a T2 crystal that we've seen many times today. And then we can do these 3 operations. I think this time, let's pick all of them. Let's transform it. Let's change the basis. Let's extend it. Yeah, let's shift it slightly. A very small shift. And then I'm going to generate my crystal. So in the middle, I've put information as to what have we just generated. Here's the scale factor. That means, I've doubled my cell length A. I've doubled C. Overall, our volume is 4 times. That looks correct. And we've also, this is 4 times the number of atoms inside our motif in the output file. Okay. And if you look carefully, they look different. From first glance, these don't look like the same file. The numbers are different. And I've just generated a new one, and a new one, and a new one. I could go on. Back to the presentation. So these are quite small. I've got an example that I've taken snippets of and enlarged so you can see clearer. Little game, spot the difference between these 2 files. I think you'll find you can guess where this is going, but the numbers are all different. I'll give you a clue. The cell volume is exactly the same. It's the same crystal. What I've done here, this is the input on the left, and I've just changed the basis, and it's no longer a right angle. Right angle's on the right. Here's the same one from different angles. So I had no extension this time. I just changed the basis and I shifted the atoms randomly. Okay, this is a different transformation. I'm calling this disguising. So it looks like a different file. It's actually very similar. It's a near duplicate. This time I doubled the cell length B. So I don't know if you can see the black unit cell line. It's doubled this time. You can see it here too. So there are more atoms displayed basically. Not changed any of the angles. And Again, I've shifted atoms randomly, and we can see that in the file. The length is doubled, the volume's doubled, and there are double the amount of columns. Okay. This is T2 alpha. On the left is the input. On the right is I changed the basis, I doubled cell length B, and I shifted some of the atoms slightly. From first glance, I don't think it's particularly clear. I mean, you can see, I don't know, molecules, but you can't tell exactly this is the same as what's on the left. It's only when I apply Mercury's, I think it's called packing, then you can see that distinctive shape comes up. Here's another example. Again, from first, if I just look at the files are completely different. I open it in a visualization software. From first glance, it looks different, but I'm tricking you, they're the same. Because when I manually add some more molecules when you click on the hydrogen bonds manually, then you can start seeing this shape coming up. There are more examples I could go on, especially imagine I changed the colors of the atoms and pretended they were different elements. You could go, but these are all near duplicates. They're practically the same geometry. I think the top you can see I've extended it. This one, not quite clear. I think I changed the basis here. Why stop at those examples? I can generate loads. I could generate thousands, millions. How about 2.2 million like GNoME did? I've got a rough estimation that it takes, if I was to generate these, it'd take what? 16.9 hours, which isn't that bad on a modest laptop. And I definitely know that the code could be written much better. My excuse is that I just finished school. I'm starting my undergraduate maths course at UCL in about 2 weeks. I've not started yet. My programming isn't the best, but hopefully in a few years when actually, you mentioned vector mathematics. I really should have put things in a matrix rather than using nested for loops. But yeah, that would make it much faster. But even with that, you can create lots of differently looking files really, really easily. I think that was the point, really, of this entire project. It's not impressive by itself to just generate millions and millions of files. You see blogs from Google saying, look, we've created millions of files. I don't care. Show me why that's important, why that's interesting. All new creations must be analyzed thoroughly. And my program has shown how easy it is to just generate millions of new looking files that are actually just duplicates or near duplicates. I guess the benefit of my program is that all my files are guaranteed to be real. We don't know about GNoME, but mine is definitely real because they're just the same crystals. And secondly, in order to compare these crystals reliably, we need to use a metric that changes continuously under perturbations. Because I shifted some of the atoms, it's important that we can identify near duplicates as well as exact duplicates. Okay. Thank you to Vitaly for supervising the project. Thank you for listening.
Thank you, Tatiana.